I don't know.
Maybe a quick one, I guess. Yeah.
Well, Morris Herlihy, celebrated researcher. You probably all know him. Great contributions to things that are far-ranging from transactional memory, let's say, to now we'll hear about smart contracts. And I will let him give a quick introduction and give us a talk. And then I can say a little more, because this is an AMA session. So we hope to have more of a dialogue with the speaker than just a regular talk. So I will try to introduce and ask some questions during the AMA that will follow. Please.
I'm going to be talking about speculation in smart contracts. This is joint work with my colleagues at Algrorand Research. Shown here the way I always see them. This is Victor Luchenko, Jing Chen, and Lubashvira. Today I'm going to be talking about blockchains. Now, blockchains may seem like a complicated and mysterious subject, but really it's very simple. A blockchain is a distributed ledger. A ledger is just an append-only list of events. Append-only means we never overwrite or delete anything. We just add more and more events onto the end of the list.
Okay, we seem to be having some technical issues. Everyone seems to have lost the sound. Can we check if the video...
Blockchains are things called smart contracts.
Oh, if we could please go back then for about 30 seconds.
A way to implement a distributed ledger, which has the admirable property that everyone agrees on the content of the ledger. Everyone who looks at the ledger can agree on what the ledger says, even if the parties sharing the ledger don't trust one another. And in particular, ledgers are tamper-proof. If you try to delete or change something, either what you do has no effect, or it turns out everyone can tell that someone has messed with the ledger content. Now, one of the major popular uses of blockchains are things called smart contracts. Now, let's state up front that the term smart contract is really a kind of marketing term. Smart contracts are not particularly smart, and they are in no way a legal contract. In fact, they differ from legal contracts in extremely important ways. Instead, you can think of a smart contract as an automaton that can own and trade electronic assets. The best analogy is a soda machine. Alice can put a dime in the soda machine, and in return, she gets back a soda. Now, the interesting things here are that there is no active agent inside the soda machine. The functionality of the soda machine is thoroughly understood by Alice. Alice trusts that the machinery works. So a smart contract is the same thing, except that instead of paying a dime, you might pay in some form of cryptocurrency. And in return, you might get securities, you might get electronic tokens, stable coins, cryptocurrencies, anything whose ownership can be represented electronically. Now, smart contracts are attractive to a lot of people because they're programmable. Programmable means flexible. Early blockchains, you could transfer money from one person to another, but you couldn't really do anything more complicated. By allowing smart contracts to be programmable, you effectively have a kind of programmable money, programmable flow of money. Because the source code of smart contracts is clear, it's transparent in what they do, at least in principle. You can look at the code of a smart contract and know exactly what it's supposed to do. If it does something you want, then you can interact with it. So this means that you can trust a smart contract even if you don't trust the other parties that you're interacting with through the smart contract. Smart contracts are used as a foundation for all kinds of decentralized applications called dApps. Now, the first thing that I want to say is why research on smart contracts is interesting. Even if you disregard everything else I have to say in this talk, this is one point that I want to get across. This is a new and exciting and somewhat immature area, which means that this is not something for specialists. You need at least a little bit of generalist chops to be able to work here. Now, the first area where you need to do some thinking is programming languages. So programming languages for smart contracts are inherently different from normal programming languages in kind of unexpected ways. So they have to be transparent from the top to the bottom so that traditional concerns like information hiding and modularity are either less important or downright bad. So in a regular language, you can use strings without knowing how they're implemented. You can use cosecant libraries without knowing how cosecant is computed. In a smart contract, you have to inspect the code very carefully because you're using it to trade money and other assets with people who would just as soon pick your pocket as not. In regular languages, Turing completeness is almost always taken for granted. Anything that can be computed by a C program or a Scala program or a Go program. Now, this is slightly controversial in some circles, but it turns out that providing the full power of Turing completeness in a smart contract programming language is actually not such a good idea. It's a little bit like giving a machine gun to a monkey. They may get spectacular results, but not necessarily the results that you're looking for. And even seemingly minor things like non-determinism. You want to know exactly what your smart contract is doing, what it's going to do. And non-determinism is a bad idea, both from a narrow technical sense to a kind of philosophical sense. And finally, a lot of very clever and convenient features of modern languages like indirection, dynamic dispatch, and so on are usually considered harmful in smart contract programming languages because you want to be able to see pretty much statically what's going to happen. So anything that dynamically changes the flow of control is pretty much evil in this context. Again, some people will complain vociferously and disagree, but that's not just my opinion. I think it's pretty broad opinion in the field. Now, the first thing you should be worrying about when you write a program is correctness, especially if your program is controlling lots and lots of money. So blockchains are notorious for providing, at best, weak consistency conditions. Under some circumstances, they provide sort of no consistency. Now, a problem with a lot of smart contract work is that the contract itself is the specification. So having your program source be the same thing as the specification means that there are no bugs. It's never the case that your program can depart from its specification because they're the same thing. This leads to situations where someone can steal millions of dollars from you and you can't convict them of a crime because, after all, you both agreed to this program and it wasn't your fault. You missed the fact that this program had a bug. If you had a specification distinct from the implementation, then you might have some grounds for complaint. Another difference between correctness conditions, this is a practical distinction, not really a formal distinction, is that your programs are subject to determined attack. You might be okay with an operating system kernel that has a latent bug that only gets triggered once every 6 years. But if you have a latent bug in a smart contract, there are armies of people sitting in cafes all over the world whose lives will be changed if they can exploit your bug and steal all your money. So this is something where any hint of ambiguity is potentially extremely dangerous. And if something does go wrong, you have no recourse, no courts, no police. This is complete, libertarian paradise where if somebody can do something, they can do it, and there's nothing you can do to get back at them. At a lower level, you can think of smart contract runtime as a database runtime from hell in some respects. There are a lot of issues about which steps should be atomic. Smart contracts can be used for very complicated swaps and options and other financial instruments. The parties participating don't trust each other. The contracts could be written by different parties. And so the question of which events should happen atomically and which don't need to be atomic is central to reasoning about these and to implementing them. Sometimes you need nested atomic transactions. Similar questions arise about which steps should be durable and what does durable mean in this context. Some blockchains lack finality in the sense that something might appear on the chain, but unless it's there for a long time, you can't really be sure because it could be displaced by something. Smart contracts pose unfamiliar trade-offs between security versus efficiency. If you're moving hundreds of millions of dollars around, then you should be willing to sacrifice a fair amount of efficiency to get a little bit of security. This is in contrast to many normal situations where you might make different choices. Another area is operating system-like properties. Arguably, smart contracts are the operating system runtime from hell. You need to find a policy to select and vet transactions from a pool. So the clients submit their transactions to the blockchain, things that they want to appear in the ledger, and the runtime system has to select which ones, has to check that they're in fact legitimate. And this raises all kinds of issues that are, some of them sound familiar, worrying about priority, batching, and recovery. But in this context, they have a fairly different flavor from the way that they appear in most operating systems work. And there are lots of other issues that rarely arise in operating system kernels, things like censorship. Can a powerful corporation or a powerful government suppress certain kinds of transactions? The parties that make the blockchain work don't all work for the same organization. Sometimes they work for themselves, sometimes they're untrustworthy. How can you provide incentives to guarantee that they do the right thing most of the time? There are lots of trade-offs, again, between fairness and efficiency, which would be made in one way in normal systems, but would probably be made in very different ways in blockchains. And finally, there's my favorite, the impact of blockchains on distributed computing. Now, this is my opinion, and this makes some people angry when I say this, but a lot of work, particularly early work in blockchains, has been essentially reinventing well-known constructs from classical distributed computing. Now, to some extent, this is a good thing because it's a new lease on life on stale algorithms. It demonstrates that the work of people in the POD-C community and so on are still relevant. It's breathed new life into entire fields like Byzantine agreement. Before blockchain and before similar things, Byzantine anything was viewed as the epitome of useless distributed computing research, and now Byzantine algorithms control the flow of literally billions of dollars around the globe. This is very satisfying. A lot of network-related issues, broadcast gossip, except that instead of sending packets around, we're moving money around with everything that implies. And a lot of the bugs and exploits that have made headlines in the past couple of years, where someone exploits a weakness in a contract design to steal tons of money, although these were viewed as wild and exotic at the time, it turns out that a lot of them were well-known concurrency bugs. The famous DAO exploit, where $50 million were stolen through a reentrancy attack, is actually nothing but a monitor invariant bug, the kind of thing that we teach undergraduates. So there's a lot of distributed computing work that can be applied to blockchains. Often it has a slightly different flavor, and often it produces new challenges. But I think this is a wonderful playground for people who want to work in distributed computing and smart contracts. So the field of smart contracts lies in the intersection of all these fields. And as I said before, this is not work for narrow specialists. This is something where a little bit of generality goes a long way. And even if you disagree with the technical content of the rest of the talk, I want to leave you with the message that whatever it is you're doing, there's probably an interesting application to blockchains, distributed ledgers, and smart contracts. So let's talk about smart contracts. So the bread and butter of most distributed ledger systems are simple payments and transfers, nothing fancy. Bitcoin, for example, basically all it does is it transfers Bitcoin from one account to another. There's some bells and whistles, but for the most part, it's just moving money from place A to place B. The same holds for privacy coins like Zcash and so on. So it's mostly transfers, it's fast, it's built in, nothing special needs to be done. And the blockchain typically checks static properties, like if Alice wants to transfer money to Bob, does Alice have any money? Now, in Algrorand, they've embraced this approach and built in a lot of even more powerful primitives in layer one. For example, there's a simple scripting language, a little bit like Bitcoin script, except much more powerful. You can take groups of payments and glue them into one big atomic transaction, something you can't do in many other languages. There are user-defined assets and tokens, similar to provided by Libra, things that would need to be defined at so-called layer 2 in many other blockchains. And there are built-in programs that will do simple things like swaps, auctions, and so on. So here is a very simplified architectural view of just about any blockchain, but the Algrorand blockchain in particular. On the right side, there's a pool of transactions that have been submitted by clients to the blockchain. They are represented as tropical fish. In the middle, there is a consensus committee that decides which of these submitted transactions are listed on the blockchain. The blockchain is the ledger. It's divided up into fixed size blocks, which are linked by hashes and pointers. This is why we call it a blockchain. This picture is a reasonably accurate picture of almost any blockchain. Some blockchains call the consensus committee miners. Sometimes they're private, sometimes they're public, but at the level of abstraction of this diagram, this works for just about anything. Now, I want to argue that despite the fact that we have a very powerful layer 1 in Algorand and in some other blockchains, not all contracts belong at layer 1. For example, some contracts are just too big. Imagine a contract that's doing a private placement of securities. This just means that I'm trying to sell you stock in a company. This company is not private, and if I want to stay out of jail, then I can only sell to qualified investors. So that means I need a large database of investors that have been vetted. They've gone through Know Your Customer, anti-money laundering, and I know I can sell securities to these people without danger the SEC is going to arrest me. I also have a database of blacklisted investors. These are investors that may have shady links or live in countries that are being embargoed, and I am not allowed to sell to them. So I need to consult these databases anytime I do a transaction to make sure I don't inadvertently do something very bad. These databases are large and sensitive, and you don't really want to post them publicly on the blockchain, not both for efficiency reasons because they're large and other reasons because they're sensitive. Another class of transactions that don't belong at layer 1 are transactions that are computationally intensive. Nearly anything having to do with privacy uses this awesome technology, zero-knowledge proofs, homomorphic encryption for databases. These are very computationally intensive, and these are the kind of technologies where every year they get astonishingly better and better and yet they're still way, way slower, orders and orders of magnitude slower than simple payments and transfers, and will probably stay that way for some time. Another class of transactions that we can't put at layer 1 are transactions that are just too weird to be built in at layer 1. My favorite example is the CryptoKitties service that appeared in 2017. It ended up bringing the Ethereum blockchain to its knees. Basically, you would buy an encrypted genetic string for a CryptoKitty that would result in a whimsical picture. You could breed them by mixing up their DNA, and people spent lots and lots of money on this. Nobody was expecting this would be that popular, and in fact, it made Ethereum almost unusable for quite some time. Technically, it's a non-fungible token with intensive computation and some secret formulas. If you don't know what that means, never mind. It suddenly appeared and suddenly faded. There's no reason to build this into layer 1 because no one could have anticipated it, and by the time you put in support at layer 1, it would have faded. Okay, finally, there's software engineering. Some contracts are just too complicated to implement at a low level, even with the scripting language. If you want to do something non-trivial, you want a higher level of language, you want to break things down into pieces, especially if you're linking together contracts written by different parties, with subcontracts are controlled by adversaries, and even building templates, that is pre-designed libraries, only goes so far. So that said, we want the ability to do some kind of programmable transactions above the blockchain layer 1. So one approach is to take it to something kind of similar to what Ethereum does. So Ethereum smart contracts have the following property. They execute user-defined code. That user-defined code can access user-defined storage. This is marvelously flexible, but we'll see it's going to introduce some problems. The validators, that is the members of the consensus committee, the agents who decide what goes on the blockchain, execute this user-defined code, and they execute these accesses to user-defined storage. And when new validators join the committee, they typically have to re-execute all the old contract calls to come up to speed. You know, there are some shortcuts, but in principle, everything is executed forever. So if we naively slap this down into our architecture, we see over here that we have a pool that consists of simple payment transactions, that's the tropical fish, and the user-defined contracts, which are the whales. The contract committee have to execute the whale's code and access its data. And so this slows down the consensus committee. It's going to take it longer to produce blocks. There's no way around this. New committee members that show up have to rerun the code. So you've got to keep the code on the blockchain so you can re-execute it forever and ever. After they've been processed, putting that code and data on the blockchain basically displaces the level 1 transactions. So you're going to get, the number of payments that you produce each second is going to be, could be substantially lower. Now, the typical response to this challenge is to say, well, we are going to let the mystical power of the market fix this. So the consensus committee says, okay, so now we're spending a lot of time and effort executing user code. No problem, we'll just charge the users for the code. This is often called the gas, as in the gasoline driving a car. So you send me a contract with a lot of computation, no problem, I charge you 10 cents for every instruction, and I'm okay because I'm compensated for all the work that I've done as a committee member. I can also cancel contracts that take too long and so on. The problem is that this completely overlooks the needs of the clients who just want to execute simple payment transactions. They've got diminished latency, throughput, higher variance, more unpredictability, but they are not recompensed by gas prices. So you're going to end up with a lot of unhappy customers. And if, like Algrorand, you're well known for your fast block time, then supporting these contracts is going to compromise that. In some sense, you're throwing out the baby with the bathwater. So how are we going to address this? Well, we are going to address this by stealing ideas. We are going to take a different approach based on speculation. The idea that most of the time things work out if you just move fast, you hardly ever break things. And when you do break things, you can go back and fix them, as long as that doesn't happen too often. So here is what an alternative architecture would look like. We are going to create a separate contract committee, which is distinct from and in parallel to the central consensus committee. So this is a separate committee, and it is going to execute all the contract calls. So it is not going to, none of these contract calls are going to go to the consensus committee. They're all diverted to the contract committee. The contract committee is going to summarize the effects of the transactions and certify them and pass them on. So the contract calls are processed by a contract committee. In Algrorand, this is chosen by the same secure randomized algorithm as the consensus committee. In any other blockchain, you could take an analogous step. Now, if you're careful about this, you can design this so that the contract committee does not actually need to solve Byzantine consensus. We do this by first publishing on the regular blockchain our intention to execute a call without actually executing that call. Once that appears on the blockchain, everyone on the contract committee agrees what needs to be done, so that all you have to do is have it executed by enough members to guarantee that at least one honest participant executes the call and can certify the results. So as a result, the contract committee is smaller and faster than the consensus committee. The contract committee could have, say, 150 members, while the consensus committee would have approximately 2,000. So this means the algorithm is faster, has less communication, and the resources needed are much smaller. So what does the contract committee do? The contract committee executes the code. It's given a snapshot of the blockchain state. So it doesn't work directly on the blockchain. It works on a current or recent snapshot of the blockchain. This is why things are speculative. After executing the contract against this snapshot, it produces a number of transactions. These are the payments that that should happen. We send these so-called effects transactions to the consensus committee, and these are only transactions. They're not. There's no user code here. They're also sending a certificate signed by a majority of the contract committee saying, yes, we executed it. Yes, these are really the valid results. I should mention that a side effect of executing a transaction of a contract call is that the contract's own data structures are updated. So the contract committee computes tentative updates to the contract storage. These updates are tentative because we don't know whether the entire contract call is going to eventually commit or abort. When the effects transaction reaches the consensus committee verifies the certificate, processes the effects transaction normally like any other transaction. When the final result appears on the blockchain, the contract committee will commit its updates to contract storage. Now, there's one important optimization I'm going to mention because this will affect a lot of different things. And that is, it turns out that the most expensive steps in this process are producing and checking certificates. These are the most computationally intensive things basically in the entire blockchain. So it makes sense to amortize the cost by batching transactions together. We're going to accumulate a number of effects transactions for a number of contracts. We're going to put a single certificate on all of them and ship them in bulk to the consensus committee. The consensus committee will then execute them one by one. So we send batched effects transactions. The contract committee checks one certificate and then processes the batch in a one-at-a-time order. And otherwise, everything works as before. So this is the big picture. The critical path for the blockchain goes from the lower right-hand corner to the upper left-hand corner. The critical path consists of these simple payment transactions which go to the consensus committee, which are packaged up into blocks. The alternative path for contracts is the contracts go to the contract committee where their code is speculatively executed. Their effects are packed into transactions which are shipped to the consensus committee. And except for checking the certification, these are treated like regular transactions. So the consensus committee needs only to be able to check signatures, and otherwise everything looks to it as if everything were simple transactions. Now, there is a catch, of course. This is central to any notion of speculation, and that is that there's a kind of window of vulnerability. So the contract committee can approve the execution of a contract, say at 1 o'clock. It then sends it to the consensus committee for execution. And let's say there's a delay. And suppose the blockchain state changes between 1 o'clock and 2 o'clock, that contract call may be rejected by the consensus committee, saying, sorry, this is obsolete, this is out of date. And that's fine, except for the fact that the entire structure does not guarantee progress. You have no guarantee if you submit a transaction that it will eventually commit, because there is no guarantee that the situation that you saw looking at the snapshot in the contract committee is the same as the situation you see when you actually reach the blockchain. Now, I'm going to explain two things. One is that this is actually perfectly okay, and the other is that this gives rise to some novel programming language or runtime constructs that we're going to look at. Now, this situation is analogous to the way people used to do finance in the last century. There used to be these things called checks. These were pieces of paper that contained promises to pay. I know that checks are hardly ever used nowadays because credit cards and electronic commerce and Venmo have pretty much displaced them. But for a long time, this is how everyone lived their lives. Now, there were two kinds of checks. Cashier's checks had the property that you could buy the check from the bank. I want to buy a car. I take my take a big pile of money. I take it to the bank. I give it to the bank, and the bank gives me a very fancy embossed piece of paper saying, we're the bank, we have your money, you can give them to somebody. You can take that to the car dealer and buy a Lamborghini with it, and the car dealer will look at the check and give you the Lamborghini right away because he's not at risk. Now, the downside is that if your bank is the blockchain, then there's only one teller and everybody has to stand in the same line. But it does have the advantage that checks never bounce. Cashier's checks are as negotiable as cash. But again, they're kind of a pain. People never use cashier's checks for everyday transactions because they were too much of a pain to get one. Instead, people would use personal checks. So a personal check was a little book you would carry in your pocket where you could write on each piece of paper a promise to pay something. And you could do this anytime you want. You could use it to pay your rent, or you could use it to buy groceries or beer. The checks, you would give the check to the merchant. The merchant would send it to a clearinghouse. The clearinghouse would pay the merchant, except sometimes it would turn out you didn't have money after all, and checks would bounce. And the fact that checks could bounce was always a possibility, but in fact, checks rarely bounced, because if everybody was worried about bouncing checks all the time, then no one would have used them. But in fact, most of the time, people used personal checks all the time. Often you had to show an ID, and they would look up your name on a list of deadbeats. But as a practical matter, the fact that checks were basically speculative transactions was not a problem. So I'm going to argue in the same way, speculative transactions on the blockchain are like personal checks written by mostly responsible people. For one thing, if you're most of the time you interact with a smart contract, you're moving your own assets. You're paying the contract something in return for something else. If you send money to the contract, you should refrain from also trying to double spend that money on something else while the contract is in flight. So if you display a minimum sense of responsibility, you're not going to cause your contracts to crash in the same way you're not going to cause your checks to bounce. Most of the time, you don't depend on volatile state. So if you see something speculatively in the blockchain state, that will probably be pretty much the same when you reach the blockchain, especially because this doesn't take very long. If you need to, you can get the functionality of cashier's checks by using simple mechanisms like escrows and multi-signatures and so on. So the ability is there to guarantee payments, but you end up, basically paying for that in terms of latency and cumbersomeness. So the bottom line is speculative contracts are actually okay despite the theoretical possibility that things might break. But speculative contracts open up new possibilities for control structures and programming language constructs. I'm going to talk about one, and that is something that we're going to call an on-chain predicate. So let's take, as an example, let's take the most popular and profitable kind of contract that's being used today, something called an automated market maker. Examples of that are Uniswap and Bancor. An automated market maker is a contract that's willing to trade one asset for another. So this particular one trades euros for dollars. So if you put in €1, it will give you back dollars. The rate is determined by something on the current blockchain state. So let's say Alice puts in €1 in this somewhat idealized automated market maker. The contract examines the blockchain state, computes a rate, and in this case, returns $1.10. As a side effect, typically automated market makers move the market when they do a sale. So following, as soon as Alice buys some dollars, then dollars will become slightly more expensive. So now the contract updates its rate to from $1.10 to $1.09. And of course, the smart contract isn't an actual vending machine, it's actual code. Now, what happens when we translate this somewhat idealized model into a speculative execution? So here we have the contract committee. Alice sends the contract committee a simple request saying, "Hi, I'm Alice, please convert €1 into dollars." The contract committee fires up a virtual machine to execute the code associated with the contract and the virtual machine storage. As mentioned, the contract committee works from a blockchain snapshot. It looks at the blockchain snapshot and says, according to this snapshot, the current rate is 1 to 1.1, and it produces effects transactions. The effects transactions say, okay, according to our speculative execution, Alice needs to transfer €1 to the contract. The contract needs to transfer $1.1 US back to Alice. Other fields in the transaction are the predicate, which I'll explain in a minute. The certificate saying, yes, I am the, we are the official contract committee. We're authorized to make this. And then a number of bookkeeping data, which I don't really have time to discuss. So the effects transactions are then forwarded to the consensus committee. So let's walk through one execution. The consensus committee looks at the current blockchain state, not the snapshot used by the contract committee, but the actual blockchain, and says, oh, look, yep, the rate is 1.1. The certificate is okay. The signatures sign out. The bookkeeping is okay. And the predicate that says, is it okay to execute the effects transaction is okay. So then it publishes the transaction on the blockchain, and now the exchange is complete. So let's roll back the film and consider an alternative scenario. So here the effects transaction arrives at the consensus committee. The consensus committee looks at the blockchain state and says, whoop, it looks like things have changed. So in the snapshot, it said the exchange rate was 1.1, but now the exchange rate is 0.5. Whoa, that's a big difference. Should we do the exchange anyway, given that things have changed so radically, or should we just cancel the transaction? Those are the only two choices. Either you have to execute the effects transaction or you can reject them. And this is where the predicate comes in. This is what you want to do here is a policy decision. It's not an algorithmic question. So the on-chain predicate is a predicate that operates on the blockchain state. It's produced as part of the effects transaction, and it acts as kind of a guard. It looks at the state and it says, yes, this state is fine. Let's go ahead and execute the effects transaction verbatim. Or, whoa, no, things are too different. Let's just cancel the effects transaction. So it's kind of a last-minute veto exercised by the contract writer who can control whether the effects transactions are executed or not. So one possibility is to say, well, the rate has changed. Sorry, a deal's off. That's has the advantage that it's simple and fair and easy to understand. It has a disadvantage that it's a little bit fragile in the sense that if the rate had changed by 1/1,000,000% then it would abort the transaction, all the parties would have to pay fees, nothing would be done, and your customer user experience would be diminished. You might have unhappy customers. So it makes more sense to say, well, okay, if the rate has changed a little bit, then I'm willing to go through with things at the old rate anyway, because it's not very big and I value my customer's experience. So the effects transaction is this last minute veto where it can check and see. So the rate that I'm actually paying is, say, within 10% of the real rate. So that's fine. We'll go ahead and do it. Oh, no, the rate has changed too much. Sorry, we're going to have to swallow this pill and reject. So here is how to think about this. The simplest way to use on-chain predicates is to say, if the read set, if the part of the blockchain state that I read, if any of it has changed, then call the whole thing off. That has the advantage, again, we can provide built-in predicates to do this. We don't need any program or activity at all. It gives you serializability of these speculative transactions. This is kind of the gold standard for consistency conditions. It has a disadvantage, as we mentioned, that it may be fragile in the sense that any interference at all by anyone will cause your call to be rejected. We can have a more sophisticated version where we can write the predicate in such a way to say, well, I can detect that there was some interference here, but all the interference was by transactions that commute, in the sense that the either order is fine. For example, an account balance, if credits and debits commute, provided you don't overdraw. And so you could imagine writing a predicate that says, I can see that things have changed, but actually it's okay because they commute. I still have full serializability. Let's go with that. And in the specific example that we've looked at, the automated market maker, you can define application-specific correctness conditions. And of course, reasoning about these is a little bit tricky. If you get it wrong, then bad things can happen. But on the other hand, it can give you a lot of power. And in this case, power is money. You can write a much more successful automated market maker if you're not spuriously rejecting a lot of transactions. We have formal arguments for reasoning about these things. You pick a post condition and you do a little bit of calculation. You can derive the on-chain predicate that you need to do this. And I wish I had more time to talk about this, but I see I'm running out of time, so I'll skip to the end. The idea, the high order bit is that smart contracts are awesome and you should work on them. The second order bit is that the smart contracts you work on should be speculative smart contracts, because those, I think, are the only way to make smart contracts really scalable. So that's all I have time to say. Thank you all, and I look forward to hearing your questions.
Well, virtual and actual applause. Thank you very much for the excellent talk. I guess we can turn on video and collect questions. This is an Ask Me Anything. When I was asked to moderate this, I was told it would be a traditional Ask Me Anything session. I didn't know that there would be a long talk beforehand. So I expect everyone who showed up today to have plenty of questions for Maurice Herlihy.
So can I go?
Please, Cliff.
So when the contract committee okays a collection of contracts and summarizes with a bunch of independent small fish transactions that just do account transfers, are they atomically applied, or can they
yes, they are. Algrorand gives you the ability to say, take these sequence of payments. The problem here is the word transaction is overlaid in so many confusing ways. But there are these atomic things you can do, like payments from here to there. In Algrorand, you can group them into an atomic group. And
okay, so they're atomically applied.
Yeah, definitely. Yeah, they have to be atomically applied.
Thank you.
Hi, Maurice.
Hi, Doug.
Great talk as always. Tell me if there's a revocation story for these committee-approved transactions. I'm hoping there isn't, but if there is, you'll tell me for the next 4 hours what it is.
Sorry, did you say revocation?
Yes.
What do you mean by revocation?
Suppose the committee says, "Oh, on further thought, we made a mistake."
Oh, no, the committee never revokes anything.
Good.
At the application level, maybe you can do a compensating transaction, but once something is on the blockchain, then it's there forever. That's sort of one of the big selling points, is that once it's there, it can't be revoked.
Yeah, I worry because everything that uses certificates eventually says we want to try to revoke them now.
No, I think specifically in this case, the certificates in Algorand specifically, all of these certificates would have timeouts on them so that you can't be on the committee forever. Algorand has this very complicated way of choosing committees and reshuffling them and so on, which I didn't talk about because it's not really relevant to the point, but that is something that people worry about.
Are there other questions, especially on the talk, but also more generally? What's this?
So I have a question. Great talk, really great talk. But I have a question because I probably missed it. So at some point you said that the smaller committee will process these contracts in batch.
Yes.
Which is crucial for performance. And then all the example was we are going to do several options like serializability versus contract specific decisions. And I don't understand how the batch applies there.
So the batch is just a way of reducing the number of signed certificates you need. So a naive approach would be the contract committee takes a transaction, they vote on it, send it out. Another transaction, vote on it, and send it out. But in this case, the contract committee will execute a sequence of contract calls and then issue a single certificate for all of them. So all that we're doing there is by batching things, we're reducing the amount of cryptographic communication, computation that needs to be done, because the signature checking turns out to be pretty expensive, and the more we can amortize those costs, the better. The question about serializability and so on is a question about the individual contract calls. So when we say
so it's not like it's an atomic block of transactions.
A single contract call can produce multiple payments which are executed atomically. The batching is not batched up atomically because we want the ability to say that if something breaks in the middle, we'll commit up to here, we'll throw out the culprit, and then maybe we'll rerun any later transactions that have been aborted because they depended on the bad guy. This is something that there wasn't really time to talk about. But
Thank you. Now it becomes very clear. I thought that the whole batch of transactions or the whole batch of contracts would be aborted.
No,
makes sense.
Yeah. No, we try to be as resilient as possible. Sometimes, one of the side effects of having batches is that unwinding failures becomes more complicated.
Yeah. Thanks. Great talk again.
I'd like to also reiterate that it was a fantastic talk, a great introduction, I felt, to the entire area and to the work. But I'm trying to understand the concurrent execution idea, especially for Ethereum. And maybe that's not the right setting. Maybe you have some more generalized model in mind. But I have difficulty seeing the value for Ethereum because miners, for instance, will spend most of their time just solving cryptographic puzzles. So I don't know, it's 9 seconds between blocks. Probably executing transactions takes a few hundreds of milliseconds. Like I would expect probably under half a second. So of those 9 seconds, the vast majority is probably trying to find the right hash to get the next block. Maybe I'm wrong in this, but that's my impression. So for miners, doesn't seem to make sense. For full nodes who will replay everything, right now the blockchain for Ethereum at least is so enormous that it's all IO dominated. Again, transaction processing is a smaller part. So at least my impression was that everyone who tried to do parallelism in transaction processing for Ethereum thought that this was not a high payoff bet. But please, if I'm wrong or otherwise, what would be the alternative setting where it would have a lot higher value?
So in proof of stake blockchains like Algrorand, where they're basically doing Byzantine, it's a public blockchain, unpermissioned, but it's doing a form of a Byzantine BFT agreement, which is much faster than proof of work. So under those circumstances, the amount of time you would spend executing transactions becomes more significant. So in some sense, proof of work covers up a lot of sins because it is so crushingly inefficient that it almost doesn't matter what else you do. But in a blockchain like Algorand or possibly Hyperledger, Libra, anything like that, we think that this structure would make more sense.
And then maybe the second objection might kind of apply. That's a great, that's proof of stake. I believe you. It probably makes a lot more sense for miners. The second objection might then apply that once that blockchain becomes really successful, once the state is in the hundreds of gigabytes or terabytes, that just going back and looking up the state of the transaction will make the IO cost be by far dominant. So it won't matter so much if you're completely IO bound. But I guess online transaction processing, while a miner is doing it, will not saturate IO anyway. So yeah, it would probably make sense.
Well, I do think that one of the technical challenges moving down the road is how we're going to keep the contract state in a database which is distinct from the blockchain database, and how you replicate that and prefetch things without violating security and so on is still kind of an open question. We can do it for what we need now because it's frankly not all that big, but it's true that if this is wildly successful, then there will be some very interesting scaling problems down the road.
So do you think all these places in Iceland will trade their GPUs for huge I/O devices that can withstand this?
Well, I think all these GPUs in Iceland are basically bitcoins and its relatives,
Right.
which is this proof of work. And not everyone may agree with me, but I think proof of work is ultimately doomed because it's just too inefficient and too awful. And that if you it's there because it's already there and well established. But if you could reboot everything now, knowing what we know, then I don't think people would use proof of work, for all of these reasons. So I'm not saying it'll go away, but I'm saying that isn't really the future.
Yeah, I think those of us with some distributed computing background are so certain of it we don't even take it seriously. On the other hand, the response people get for our Algrorand and Libra of the notion that there are chosen fews, it's going to take a while for people to get used to it, I think.
Well, there is Bitcoin started out with this very pure ideological view of the world. And as it runs into contact with the real world, you have to make kind of sensible compromises. So Libra is based on the idea that a bunch of corporations who don't like each other will be fair regulators. Algorand is based on any random person who wants to participate who's chosen by this verifiable random function will work. And we'll see what happens with Libra. So far, Algorand is doing okay with their approach. You can run an Algorand node on a Raspberry Pi.
Which makes for some fun student projects.
It does indeed.
So I could continue because I have lots to ask you. So first, if I could nitpick, and maybe again I got this wrong, the automatic market maker example. At least I think these days it's not really considered good practice at all for market maker contracts to consult the current state of the blockchain at all, like the state in the block. That's very vulnerable. So
that's a because my example wasn't clear. So by the state of the blockchain, I meant something exactly like Uniswap, where the state of the blockchain are the account balances. So on Algorand, all of these assets are layer one built in at the same level as the native currency. So when I say blockchain state, I mean the contract looks at the account balances that it owns and it does the math. I'm not talking about oracles or external things. So in Ethereum, the account balances would be kept in a contract local storage in a table. But in Algorand, those things really literally live at layer one on the blockchain. So that's all I meant by that.
Yeah, I think my point was that I've been very heavily involved in the Ethereum security community lately, and there are many attacks in the past 6 months have been based on that, past year really. It's not considered a good practice at all to check current balances to determine an asset's price. Like for instance, Uniswap, that was a big vulnerability in Uniswap v1 and version 2 that came out this year. The big thing that they did to fix it is that when they check a price, they don't check the balances of the two tokens that you're trying to swap that exist right now, but the ones that existed at least a couple of blocks before.
Okay, okay.
The reason for that is that now there are these mechanisms called flash loans.
Oh, yep.
Instantaneously, you can borrow a whole bunch of money and distort the market temporarily. And if you distort the market, you can make the contract think that some asset, like the dollar, let's say, if it was on the blockchain, that it's worth a lot less now. And then suddenly you can profit from that. So I just think that the example might need to be rephrased a little, because what it's protecting against, what it's saying is a sensitivity that probably these days the market makers do not want. The market makers do not want the ability to be able to base decisions based on the current prices to prevent a swap because the current price has changed. They want to rely on old data, which makes your example better in a sense for the overall policy, but not as a good example for fixing the inconsistencies.
That's a very good point. And that means I'll have to find something else to illustrate why you might want to react to things that change.
Can I throw something out here? So
yes.
I spent some years, tracking fraud in the commodities markets, and there's always this arms race. And there was a moral imperative that was understood by many people, but it wasn't obvious what that was or why they had these moral imperatives, which turned into what was fraud and what was not was highly, I want to say situational and not obvious at all. If you remove the sort of moral imperative and just say, make your profit, you get a different set of constraints you want to have on your contracts, and you defend against different kinds of attacks. And if you claim that, somebody who takes a flash loan to distort the market, there is an equivalent behavior on the CFTC that was considered fraudulent for people doing behaviors like that, and we would flag it as fraud, and they could get hauled in front of court. But it was not obvious ahead of time that was a criminal activity.
Mm-hmm.
And all I'm just saying here is, boy, there's an arms race, and they're just heading down the path where people who've been doing real money for a real long time have been down this path for a long time.
Oh, well, there's no question that blockchain world is reinventing a lot of stuff from finance and other places,
including the crimes, is what I'm saying here.
Yeah. But mixing these, it's sort of a new spicy mix of older things. No, I spoke to somebody. There was one of the first major exploits was this DAO in what was it, 2016 or 17, and I actually spoke to somebody, an expert who was interviewed by the FBI, who wanted to know, was this a crime? Because contract is a contract, and if I find a bug in the contract and steal all your money, is that illegal in any sense? And it's still not entirely clear whether
exactly. There are levels of, if you're a standard consumer, there's a level of contract for which you are defended against by standard consumer law. But if you're, I want to say, a big boy, and I have totally signed contracts which had big boy clauses in them, all bets are off. You screw it up, you lose.
Yeah, and this is the distinction between the specification and the contract that I mentioned earlier. The intent of a contract is governs any kind of little minor technicality. So this whole pound of flesh story wouldn't make sense in a court of law. Because if there's a technicality in the contract that's clearly not what it was supposed to do, then you have some level of protection, but not if it's executable code.
Yeah, exactly. You're headed for new ground.
This is
a lot of fronts.
It's why this is so much fun.
Just procedurally, I would like to just inform everyone. I was just being told that the policy changed, and in fact, our entire session is being live streamed on YouTube. Originally, we said the Q&A would not be on YouTube, so everything you say is streamed on YouTube right now.
So if I stand up without my pants on, people are going to see?
People are going to see. Well, haven't they already?
Can I get to some ask me anything kinds of questions?
Go for it.
Absolutely.
Yeah. So I, like a bunch of people, I teach a 2-part parallel concurrent network distributed course, 2 semesters, And blockchains, you know, over the past 5 years, coverage went from 5 minutes to 5 hours, I think. Do you have any thoughts of what every good systems PL type graduate should know about things? Because I don't know where to focus right now.
So I teach a semester-long undergraduate class on blockchains. And it's a bit of a challenge because, you know, there are textbooks out there which are really good textbooks, but they tend to focus too much on Bitcoin. So the one part of the class, which is basically 3 weeks of lectures, is I go through and do kind of forensic analysis of all the great Ethereum exploits and hacks. You know, there's a number of places on the web that catalog these things. And these things range all the way from, you know, low cunning to, you know, really, you know, fairly profound insights. You know, and my favorite one are honeypot attacks, where you put out a contract that has an obvious visible flaw, and bad people look at this and they try to steal your money, but they miss that there is another even more subtle flaw, which means that you end up stealing their money. So even worse people get to steal from bad people this way. And by doing this thing, you know, this illustrates a lot of programming language design issues. You know, the Solidity is a language that sort of keeps on giving in terms of really catastrophic, you know, user interface approaches. It's gotten a lot better, but at least in the early days, it was, you know, kind of amazing. And these sorts of things really intrigue students, and it's a way to convey important computer science lessons as if this were an Ocean's 11 heist movie.
Yeah, I'm with you on that. What I ask myself is, what do I want to be sure they know?
I think,
and you know, consensus, Byzantine fault tolerance, proof of stake versus proof of work are the software engineering aspects of the error proneness of concurrent distributed anything are what I aim for, and how I get there is, well, try to make it as fun as you can.
So what, you know, if you wanted, the slides for my class are publicly available on the Brown, you know, webpage somewhere, yeah. You know, and they're all Creative Commons and so on. So, you know.
Well, the first time I did a whole class, I stole your Podsy slides, of course, because they are so good. People have not seen Morris's Podsy talk on blockchains. You have a really fun hour ahead of you. It was a terrific talk.
That, you know, the different students like different things. You know, it's important, I think, to steer students away from politics and crackpot economic ideas and focus on technical things. Yeah. You know, because every now and then you get a couple of people who have very strong political opinions who want to steer the conversation that way, and that never works out well.
Yeah. Thanks.
I could also ask me anything style of questions, which is what I wanted to start with when I thought this would be a pure ask me anything session. So I think, I mean, you've had a tremendous career. I remember reading weight-free synchronization papers from you, algorithms, anything in distributed systems. And so you've done a whole lot of things over many years. And I'm curious, first, what you are most proud of? And second, what would be something that you are really proud of? You thought that, hey, this is going to be huge, and nobody ended up noticing.
Oh, I tend to sign up for a lot of fads. You know, so at one point I thought distributed shared memory was going to be awesome, and all the warning signs were there. You know, people were writing lots of papers on it, but and you keep expecting that somebody's going to go implement it or do a startup company and get rich, and none of that ever happened. So that was something, I spent some time working on that, and I should have spent that time doing something else. When I started working on blockchain, a lot of my friends and colleagues thought I had, kind of lost my sense of responsibility. But I don't regret that, because from my point of view, blockchain is in some sense the ultimate playground for distributed computing. So, Podzi has always had this kind of neurosis about nobody respects us because they think we're not practical. But if you look at all of this blockchain work, a lot of it really is, disguised, but classical distributed computing. When I was a grad student, I was at a workshop in Asilomar, where somebody, I think Cynthia Dwork, brought together these theoreticians and these practitioners. And there was one guy who was yelling at the theoreticians saying, "You guys are all abstract losers because you work on things like Byzantine agreement." And then he would practically spit on the ground. Then many years later at SOSP, I introduced Barbara Liskov when she gave the talk on PBFT. And I said something to the effect of, well, it's very satisfying to be talking to this ultimate practical conference about Byzantine stuff. And everybody just looked at me blankly. They had no idea what that Byzantine agreement was once this kind of incendiary thing. And the reaction you get when you talk to systems people are, "Hey, we invented this Byzantine stuff. Why didn't you theoreticians do it first?" But no, I'm not complaining.
I would like to continue on Yanis's question, and I would like to ask which result that was invented during your career, not by you would have liked to have invented, you have to be associated with.
Oh, well, I think there's all kinds, even something like blockchain itself, all the pieces were there. Bitcoin didn't really invent many new things. Proof of work had been proposed as a way of fixing spam. Again, the ability to see these different pieces and plug them together is something that weight-free synchronization was basically applying database principles, serializability and concurrency control to data structures. And again, all the pieces were already kind of sitting out in plain view, and noticing that there was a connection was the main contribution. And there were all these other things where you look at something afterwards and say, "Ooh, I should have thought of that." Or even worse, I almost thought of that, but then I got distracted.
So, well, if I could push back a little bit on the Byzantine stuff, it is very much a different kind of Byzantine agreement than what we learned in I don't know, at least in my graduate distributed systems classes, because Byzantine was indeed considered, as far as distributed systems were concerned, completely infeasible, not a practical thing. Like, the most feasible result was, I don't know, Lampert's 2/3 or something like that.
Yeah.
Because it seems that before crypto, nobody had even thought of, well, I can propagate someone else's message, but without anyone being able to, forge it. I can claim that Doug told me that Morris told him that Cliff did something, but the entire chain is signed. So I couldn't have forged it. And that was a game changer. And I think in a sense, the distributed systems results did not exactly apply. They were radically changed when crypto came along. Or was it not the case? Because my impression, at least from a little bit far from this, is that the moment this was realized, it was kind of a watershed event. Like within 5 years, maybe, that game had changed. Whereas before, for 30 years, Byzantine agreement was considered a certain thing, and all the results were kind of negative.
Oh, I think, well, there's two things. One is that the reputation of Byzantine suffered because for many years people were publishing increasingly kind of incremental papers in theoretical conferences, and so I remember rolling my eyes every time I was asked to referee a Byzantine paper. But I think that one thing, you're right that crypto changed a lot of things, but also the advent of practical Byzantine fault tolerance. Miguel Castro and Barbara Liskov's paper was the first paper that in some sense made a case that you could actually do Byzantine agreement. It wasn't this exotic theoretical construct. So they spoke in a language that systems people could understand. It was done by people with systems credentials. So it was kind of it broke the barrier between this sort of the theory bubble and the systems bubble, and then from that point on it sort of got taken up more and more, and now in some sense people have forgotten that this was originally lived in a theoretical ghetto.
So, brief interruption again. Our student volunteer is notifying me that the YouTube stream is going to end within 3 minutes or so. If you are watching this on YouTube, this does not apply to people here on Zoom. If you're watching this on YouTube, please go to the Meet the Speakers session on Clouder to continue watching and to ask questions. That was the public announcement. So,
and an advertisement, you can watch Cliff and me do this again in less than an hour.
Sounds like fun.
By the way, are we going to do the same thing in 12 hours? Are you going to be available for live questions in 12 hours or not?
Not me.
No. Okay.
Well, I will be asleep in 12 hours. Thank you very much.
So I don't know what I have to moderate in 12 hours then. What's my job as a ask me anything moderator? I don't know. Okay.
You're welcome to forward questions, and I don't know when and how, what the form for response is, though.
I can try to channel. Okay.
You can start a list of questions to ask yourself.
So
if they're enticing enough, I'll throw them up on my Twitter feed.
If questions don't get answers, I don't think they're that interesting. So a similar objection could be raised about the DAO hack and viewing it as a concurrency issue, I feel. So I mean, it is a kind of concurrency issue, but I think you have to squint really hard to see it as one. Like you really have to want to see it as a concurrency issue.
I think that depends on. So to me, this is a monitor invariant violation. You're inside the monitor. When the monitor is unlocked, there's an invariant, which in this case was that your variables tell you how much money you have. If you can violate the monitor invariant, and if you exit and release the lock, you better restore the monitor invariant before you leave. And the problem with the reentrancy attack was, it's not exactly 100% the same thing, but somebody managed to get inside the monitor while the invariant was broken. When you make a call, you're effectively releasing the lock and going out. And so to me, it's that's the heart of the problem. And if you're used to this kind of reasoning, then you look at this and you say, oh, of course, where are the places where you release the monitor lock? Does the invariant hold? Well, in this case, no. And so
my students don't have trouble with this because they get drilled into them. Never call a function you don't know while you're holding a lock. And so if you have that beat into your skull, like they saw it in 30 seconds. Well, the two really great students I had that semester saw it in 30 seconds.
Yeah, I mean, I should say when I say that this is an elementary error, I'm not disparaging the abilities of the people who made this mistake, because it does look very different. But in hindsight, it's basically isomorphic to this common common error.
Yeah, I agree. This is a very good analogy. I mean, it's very much like a monitor invariant. It's just that it doesn't feel like concurrency because you're handing over the execution explicitly to someone else. So is it a concurrency issue? But you're right, the analogy to a monitor invariant, you don't have to squint very hard to see it. That's definitely a very strong analogy.
Yeah, the reason it happened is because it didn't look like a concurrency error when in fact I believe it was. If it looked like a concurrency error, they probably wouldn't have done it that way.
Well, it's interesting philosophically to ask what's a concurrency error in single-threaded transactional execution. But yeah, once we decide to call them concurrency errors, then that's exactly, it is a concurrency error. Right?
Yeah, you have more than one program counter hovering over the same data.
I would say you don't, though. It's just one program counter.
No, you have the program counter stops when you make the call, and it basically suspends. The reentrant call is the second program counter.
That's right.
That comes in. So,
Yeah.
so now only one of them is actually moving. The other one is suspended, but it's still two program counters dealing with data whose consistency is suspect.
Why are they program counters? Why aren't they just stack frames and you just save the return pointer?
It's as if the OS suspended one thread right there, but it's middle of execution, and then another thread comes running in.
But
It happens in all multi-threaded code all the time.
But it is, well, okay. You could think of it that way, but you could also think of it as just a regular function invocation is what I'm trying to say. Because it is, you're calling someone by name, you're saying, well, now call this. Fine.
But if you think of it as a regular function call, then you're going to miss the bug. Whereas if you think of it as a concurrency, then the bug, at least to me, jumps right out.
Sure, but then you can think of it as regular function call and then trusted and untrusted code. You can think of it as trust zones, let's say, because that's really the issue. I mean, any explicit transfer in a single thread, if I explicitly call someone, I have a bit of a hard time calling it concurrency, but you're absolutely right. It feels exactly like a monitor invariant violation. So it's a fair view. I'm not disputing it. I'm just making small talk.
One more try. So maybe a better analogy, the cases where you're holding a lock. So don't even think about locks. You're running something. There's an exception catch, and then a finally runs after it, and the finally really did not anticipate the state that the exception catch would have put it in.
Yeah.
So this is how you get the sequential analog of concurrency errors, is by try catch finally.
Yeah, something happens, it jumps there. Your invariant is scattered across the floor in little pieces, and you don't restore it before you leave. Then, except usually when that happens, you get a blue screen instead of losing $50 million.
Yeah.
Great analogy, Doug. Great analogy. I like that one with the exceptions. Yeah.
I actually hate it because I don't like exception handling. Almost everywhere I see it, it's broken. And so almost always, if I see somebody, I'm doing somebody else's code, I'm trying to fix their bugs, and they have exception handling, I throw it all out. And if any exception ever got thrown, we can have a discussion now about how to recover. But if they wrote a handler, 99.9% of the time, it never got tested, and it does the wrong thing. Just say no to exception handlers.
Well, if you're cursed to be a library writer, we're the only people who do actually have to get those right.
But you test them.
Yeah.
And if you test them, that's okay. But people write these handlers. Sorry, I'm off on a rant sideways.
No, our smart contract VM is written in Rust, and Rust doesn't have exceptions, but everything is an option.
Yeah.
So you're matching right and left. You know, and the entire programs are big case statements.
Yeah, it's really sorry to interrupt here, but I guess it's about time for the speaker to switch to the Clouder, like for the meet the speaker session there. And if folks here can join Clouder, you guys can definitely continue the conversation over there. Yeah. Yeah, sorry about that. It's actually scheduled to start like 4 minutes ago. Yeah.
Okay.
Yeah.
Right.
So also one more thing that Professor Morris Hurley, when you finish the session, please log out of the Clouder so the next speaker, Professor Cliff, can use that account to log in for his meet the speaker session.
Okay.
Well, I can't log into the Clouder session.
Yeah, you can. Only one person can log in at the same time.
Okay. So I better not make any nested calls.
Yeah.
Exactly.
To be honest, I just joined normally, yes?
Oh, yeah, because I think